Hello friends, welcome to lecture number 41. In today's class, we'll study about how a current carrying loop will behave like a magnetic dipole. Okay, so we have taken a current carrying loop here, and here the current is moving in this direction. Followed, and we have assigned an axis x, y, and z axis here. In x axis, we have taken a point P, and this point P is situated at a distance x from the center of the current loop. Okay, and what is the radius of this current loop? It is capital R is the radius of the loop. Followed. Now at point P we need to calculate what is the magnetic field, and we have already discussed this derivation also. Okay, so what will be the magnetic field? So the magnetic field along the axis is given by we have already calculated, B is equal to mu naught I r square divided by 2 times of x square plus r square to the power 3 by 2. And what about its direction? Its direction will be along the axis of the coil. That means it will be along this direction. B vector will be along this direction. Okay, so we can write here along the axis of the coil. Along the axis of the coil. Okay, now for large distance, at large distance, it is quite obvious that your x will be much greater than r. In that case, I can neglect r square in the denominator. Okay, so what it will be? It will be mu naught I r square divided by 2 times of x cube. Okay, so now let me multiply pi on both numerator and the denominator. Pi r square divided by 2 pi x cube. I am doing it intentionally because this pi r square will be your area of the loop. Okay, so here pi r square will be the area of the loop Okay, so I can now replace pi r square by a quantity which is a. Clear? So B will be equal to how much? B will be equal to mu naught I a divided by 2 pi x cube, where a is the area of the loop. Okay, again let me multiply and divide by 2 here. So what I'll have, B will be equal to mu naught by 4 pi. I am doing it intentionally just to have a comparison, into 2 times of IA divided by x cube. Let me give it as equation number 1. Okay, now if you remember in chapter number 1, when we had found out the electric field on the axis of a electric dipole, that expression we will be using. Okay, so we have calculated the electric field on the axis of an electric dipole. If you remember properly, the expression was E is equals to 1 by 4 pi epsilon naught into 2 p by x cube. If I write it vectorially, it will be this. It is equation 2. Now if you compare equation 1 and 2, comparing equation 1 and 2, if you compare both of them, it is quite obvious this P, which is your electric dipole moment, will be equal to IA. Okay, both of them will be equal. Clear? So what we can say, that looking into the comparing equation 1 and 2, what we can have is I into A is the magnetic analog of the electric dipole moment, that is P. Okay, so therefore IA will be named as the magnetic dipole moment and is represented by M with a vector sign. It is a vector quantity. That is I A vector. I have already told you area is going to be a vector quantity while I have taught you flux. Okay. Now what is this M vector? It is your magnetic dipole moment. Magnetic dipole moment. Okay. Clear? And what about its direction? Same as the direction of the magnetic field. That is, it will be your magnetic dipole moment direction will be from south to north inside the magnet, and it will be from north to south outside the magnet, Okay. So we can say here the magnetic field produced by a current loop is identical with the electric field produced by an electric dipole. So finally we can say, hence we can say that the current loop is equivalent. It comes for a 2-mark question. Equivalent to a magnetic dipole. Okay, so I hope it is clear. This comes for a 2-mark question. Now we will apply this magnetic dipole moment when for the revolution of electrons. We know inside an atom electron revolves around the positive charged nucleus. Since electron revolves, it will be revolving in a circular path. We know it from Biot-Savart law, from your Bohr's atomic model. Okay, so if it is revolving in a circular path, the electron, then it will be behaving like a current loop. Okay, let's see that how we can assign magnetic dipole moment for a revolving electron. So the next topic of discussion will be your magnetic dipole moment of a revolving electron. Okay, around the positive charge nucleus. We'll look into this. Followed. So in this case, what we'll do, we will consider the circular path of a electron. We'll consider the circular path of the electron, and the electron is going to move in which direction? It moves in this direction. Okay. So basically, this will be your motion of electron. Since it moves in a circular path, the radius here we'll take it as small r. Okay. So from Bohr's atomic model, we know that electron revolves in a circular path. Okay. Then what will be E? Is the magnitude of electron. Then what about T? Capital T is the time period. It is the time period of revolution. Okay. Then what about V? V is velocity of the electron. Okay, velocity of the electron. Now, if I want to calculate the current is nothing but charge per time. So charge means whose charge? Electron divided by time t. Okay. Now, what about the velocity? Velocity will be distance by time. So what distance it is covering? 2 pi r circumference divided by t. So this implies t will be equal to 2 pi r by v. So I will substitute this value of t here. I'll substitute here. If I do that, what will be the value of I then? I will be equal to E divided by 2 pi r divided by V. Okay. Then I will be equal to EV by 2 pi R. Clear? Now the magnetic moment produced magnetic moment produced by the revolving electron is given by mu L. Okay, mu L. So the magnetic moment in case of electrons will be represented by mu L. And what is it? Current into the area. So what is the value of current you have calculated? EV by 2 pi R. And what about the area? Pi small r square. So how much it will give you? It will give you EVR divided by 2. Okay, pi gets cancelled out, RR gets cancelled out, so EVR by 2. So mu L will be EVR by 2. Okay, now dipole moment has a direction. Now we need to find out what is the direction. And moreover, this mu L, to be very specific, it has got a name. It is called orbital magnetic moment. Okay, so coming to the picture which I have drawn here, you see here the motion of the electron, it is in anti-clockwise direction. Okay, but mu L depends on current, so the current direction will be in clockwise direction. So you use your right hand thumb rule. Current will be in clockwise direction. Where is the thumb pointing out? It is quite obvious. The thumb is pointed downwards. So mu L will be in downward direction. That will be mu L vector. Is it understood? Don't confuse. Mu L is not due to the motion of the electron. It is because of the current. So current direction you will take in order to know the direction of mu. Okay. So finally I can write here mu L and I can put a cross here. Cross indicates what? It is into the plane of the paper. Okay. Orbital magnetic moment understood. Next we will go for the expression for gyromagnetic ratio. Okay, we'll go for the expression of this. Clear? So what we have found out till now we got that your mu L is equals to EVR divided by 2. So let me multiply the mass of the electron on both the sides, up and down. EVR, mass of the electron, divided by 2 into mass of the electron. So what is ME? ME is the mass of electron. Is it clear? So if I do that, but we know that mass of the electron V into R, what is it? It is capital L. And what is L? L is your angular momentum of electron. Okay, so let me substitute this value. If I substitute this value, your mu L will be equal to EL divided by 2ME. Okay, so this is only the scalar, the magnitude representation. But if you look into the vector form, for that again we will follow the diagram. You look at this diagram. In this diagram, you can easily find out that your L, that is the angular momentum of the electron, it depends on the motion of the electron. And motion of the electron is in anti-clockwise direction. If you use the right hand thumb rule, anti-clockwise direction, thumb is pointing upwards. Okay, so your L direction will be upwards. Is it clear? Mu L will be downward, which will be, you can find out because of the direction of the current, and L you will find out using the direction of the motion of the electron. L is up, mu L is down in our case. Okay, so vectorially, and it is quite evident that both of them are in opposite direction, L and mu L. So in vector form, how can you represent in vector form? In vector form, you can write your mu L vector is equals to E by 2ME L vector with a negative sign. Why this negative sign? because mu L and L are in opposite direction. Okay, so you can mention here the negative sign. The negative sign indicates the negative sign indicates that the angular angular momentum of the revolving electron is opposite to its magnetic moment Okay, so if you take the mod of mu L divided by L, if you take mod, this will give you E by 2me. Okay, and this mu by 2L is the gyromagnetic ratio. Mu L by capital L is your gyromagnetic ratio. And what is its value? Its value is 8.8 into 10 to the power 8 coulomb kg inverse. Okay, so basically gyromagnetic ratio is the ratio between magnetic moment of the electron to its angular momentum. Okay, now the last topic for today's class will be your Bohr magnetron. It will be your Bohr. Sorry, one second. It will be your Bohr. Bohr is the Niels Bohr who gave the atomic model. Okay, that we'll read in detail in atom chapter. Bohr magnetron. Okay. Now for this Bohr magnetron, we will take the help of the second postulate of Bohr's atomic model. What is the second postulate of Bohr's atomic model? And we know from Bohr's postulate for quantization of orbits, your angular momentum, which is mvr, is an integral multiple of h by 2 pi. Okay, where h is what? H is your Planck's constant. It is your Planck's constant. Okay, so what we have mu L is equal to E by 2me into L. Now instead of this L, you can write nh by 2 pi. Okay, so what we'll do next? It will be your E by 2 to the 4 pi me into nh. Clear? Then the minimum value of magnetic moment, orbital magnetic moment, is obtained by putting what value for n? Obtained when n is equal to, yes, n is equal to 1. Okay, so when n is equal to 1, your mu L minimum is equal to how much? EH by 4 pi me. Okay, this mu L minimum is known as your Bohr magnetron. Okay, and this is nothing but Bohr magnetron is basically the unit of atomic dipole moment. Okay, now let us see what is its value. Okay, let me put all the values, EH, 4 pi me, everything. So we can write putting the values, your mu L minimum is equal to how much? E means 1.6 into 10 to the power minus 27. Then H value is 6.63 into 10 to the power minus 34 divided by 4 into 3.14 into 9.1 into 10 to the power minus 31. So if you solve this, you will be getting your mu L minimum will be how much? it will be equal to 9.27 into 10 to the power minus 24 ampere meter per meter square. No, not per meter square, multiplied meter square. Okay, so this is the value. Got it? So this is all about for today's class. I hope all of you must have enjoyed it. Do not forget to subscribe my channel, which will motivate me to give further topics of class 12, further physics topics. Okay, so for any queries you can mail me in the mail ID which is given below. Thank you.